The Wooden Warrior, a glider by me, Andrew Burgess. The objective for this project was simple: to create a glider from household items capable of traveling upwards of 20 feet. An appropriate measure of success for the glider is its quality of performance during the test flight, including its distance flown, stability in the roll, pitch, and yaw dimensions, and its durability in surviving a landing. An additional requirement for the glider was that it needed to fit within a 16 by 16 inch square. The first design decision that I needed to make regarding my glider was its intended material. While cardboard would be abundant and cheap, this material is flimsy, and cardboard wings would sag under their own weight for large gliders. Rather than completely scrapping this material, I decided to utilize its abundance to create a half-size model to experimentally test parts of the glider's design. Carbon fiber, which is used for many real-world gliders, is unfortunately too expensive to be used for my glider. For the full-size design, I decided to go with the balsa wood that I was given for the project. Despite being less readily available than cardboard, balsa wood is the ideal material for achieving the project objective due to its unique, lightweight, yet sturdy nature. For the wing shape, I debated between elliptical, rectangular, and tapered planforms. While the elliptical is the most efficient, this shape would be difficult to make using only uh, the balsa wood. Rectangular would be very easy to construct, but is far less aerodynamically efficient due to its constant chord length. The best of the three options is the tapered wing shape, which will allow the glider to generate more lift during its flight. The tapered shape allows for the wings to maintain a high area while still having a lower average chord length than a rectangular platform, resulting in a higher aspect ratio. While sacrificing the efficiency of the elliptical wing, this shape would be easy to manufacture and would ultimately help my glider achieve its 20-foot measure of success. The goal when creating an object that flies is to maximize strength while minimizing weight. While adhesive like wood glue and hot glue are very strong, they are also heavy. Including them in my glider might cause uneven weight distribution, leading to instability and failure to reach 20 feet. The alternative is regular masking tape, which is slightly less strong but much lighter. My initial concept was the result of considering the pros and cons of my various alternative design options and deciding on the features that gave my glider the highest probability of success. My initial glider design was made entirely of balsa wood due to its strength over cardboard. I had to ensure that my glider had an aspect ratio between 4.5 to 7.5, as recommended by the Milwaukee School of Engineering. To do so, I decided to make my wings as long and skinny as possible, without making them too weak. I chose to use all 16 inches available for the wingspan. The wings in my design had a root chord length of 2 inches and a tip chord length of 1 inch, and were located 4 inches behind the nose. I also planned to include a slight dihedral. Because the length of a glider's fuselage is supposed to be 4 to 6 times the length of the chord of the wing, and my planform had a root chord of 2 inches, I chose to make my fuselage 12 inches long, which places my glider at the upper limit of this guideline. The tail configuration consisted of two parts, a vertical stabilizer and a horizontal stabilizer. During manufacturing, I planned to make the area of the horizontal stabilizer roughly 20% of the area of the wings, and the vertical stabilizer about 10% of the area of the wings, as suggested by Pittsco Education. I eventually settled on the lightweight yet strong masking tape as the adhesive for the majority of my glider. The only location that required hot glue to remain in place was the vertical stabilizer. Here is a side view of my initial design in which the intended dihedral is visible. Included here are photographs of my initial cardboard models that vary in the presence of added weight on their noses and the shape of their horizontal stabilizers. Included here are photographs of cardboard models that differ in their wing positioning. The left is flat, while the right has a slight dihedral to increase stability during flight. These are the first test flights of my initial models, in which extreme longitudinal stability issues can be observed. Furthermore, these flights are not nearly 20 feet, which does not satisfy the project requirements. In these flights, you can see the glider veering to one side and sometimes simply slamming straight into the ground. To address these problems, I made the following changes to my glider before making my full-scale prototype. Number 1, I added weight to the nose of my glider. Number 2, I moved the wings up to 3 inches from the nose. Number 3, I gave the horizontal stabilizer a tapered leading edge. These first three changes were implemented to counteract the stability issues observed in the test flights by shifting the center of mass toward the nose. I found that the glider not only had fewer pitching issues, but also flew further with a tapered front edge on the horizontal stabilizer. Number 4, I changed the orientation of my vertical stabilizer to increase its strength, as seen in the photo on the right. Number 5, I removed the dihedral. When testing my cardboard models, I found that the inclusion of a dihedral in my wings improved its horizontal stability. At the Aero Makerspace, however, a classmate of mine showed that their dihedral wings actually made their flights worse. Because of this, I decided not to use a dihedral in my model. Here's a full-scale prototype of my glider with the changes I made after testing. On the left is my best test flight for my final design. I believe that this length of flight was achieved due to the updated shape of the horizontal stabilizer, improved wing placement, and added weight to my nose cone. On the right is my cardboard model's best flight at around 25 feet, which was achieved after finding the perfect amount of Play-Doh for longitudinal stability and including a tapered horizontal stabilizer. The center of gravity for my glider was located about 0.5 inches behind the quarter cord of my wing. At this location, the glider was able to balance on my finger as shown. Because the quarter cord is often referred to as the aerodynamic center of the vehicle, having the center of gravity lie close to this point is important for stability. For my glider, the center of gravity lies behind the point to account for longitudinal stability and to offset any unwanted pitching that was observed during testing. By plugging in the measured quantities into the equation as shown, we can calculate my glider's lift coefficient to be 0.0988. Using the equation for induced drag on the right and multiplying by 2 yields a total drag coefficient of 0.000824 for my glider. Here is proof that my glider adheres to the project specifications and fits within a 16 by 16 inch square. If I had to do this project again, I would try to get as much balsa wood as possible so that I could create my testing models out of this ideal material. I would improve my design by altering my tail configurations and by placing the horizontal stabilizer above the vertical stabilizer as seen in this image. I would also try to set up my own flight course to minimize outside variables such as temperature and wind speed and direction. Overall, this project was very enjoyable and allowed me to actually apply the concept of aerospace engineering that we've learned this semester. Here are the sources I used for this project. Thank you.